All right, hey guys, here is our first lesson in our probability distributions lesson. This is chapter 7 of your textbook. It is our 6th unit of data management. First of all, some definitions for us. An outcome. Many probability experiments have numerical outcomes that can be counted or measured. So these are the things that we are looking for. All right, a random variable. We use a capital X to define the random variable. It has a single value that we call a lowercase x for every outcome in an experiment. Okay. So for example, if we look at a dice game, each face of the die corresponds to a single value or an outcome. Okay, so that's the things that we're looking for in the experiment. Okay, so in this case, there are 6 different outcomes of the game using a single roll of a single die. All right, now if we remember back to our initial probability units, we looked at discrete variables and continuous variables. So you should remember that discrete variables are things that are separate from each other. So for example, a dice roll, it can be a 2 or a 3, but it can't be a 2.5. Shoe size could be size 9, 9.5, or 10, but I can't be a 9.3. Number of people has to be a whole number, all right? So these are discrete values. I can't get values anywhere between these numbers, all right? Discrete values can also be limited. So for example, a dice roll falls in the range of 1 to 6. It can't be a 0 or a 7. In comparison to this, continuous variables can be any value within a range. So for example, height. I can have one person who is 161 centimeters, but someone else could be just a tiny little bit taller than them. They could be 161.3 centimeters. Or if I get even more accurate, I could have someone who's 161.375 centimeters. So I can actually have any value between actual whole numbers there, okay? So temperature, crime rate, speed, all of those are examples of continuous variables. Just depends on how accurately we measure. Continuous variables can also have an infinite range. So if we consider distances, if we look at the width of an electron versus the distance of Neptune from the sun, we've got very different measurements there. All right, now a probability distribution. We've looked at single probabilities before, but a probability distribution now is where I look at all of the possible outcomes and the probabilities for each of those outcomes in a specific experiment. All right. So our probability distributions, we normally look at 2 ways. We either look at as a table or we look at it as a graph. All right. The graph is usually a bar graph, which we would call a probability histogram, just like our frequency histograms that we did in our one variable statistics unit. All right, so here we are looking at the theoretical probability of rolling a single die. So I've got 6 outcomes. They are the rolls. I roll a 1 or a 2 or a 3, 4, 5, or 6. The probability of each of those outcomes is 1 out of 6, as long as I have a fair die. So this particular scenario here is known as a discrete uniform distribution because the probability of each outcome occurring is exactly the same as all the others. All right, so this is, again, a discrete uniform distribution. Uniform meaning it's the same. You can see in my probability histogram over here, all of the probabilities are exactly the same. Now, in this case, we have a company, Best Buy, has tracked the number of computers that they have sold over the course of a month, and we can see how often that many computers were sold. So 3% of the time, the probability of 0.03 is 3%. So 3% of the time, they didn't sell any computers. 7% of the time, they sold 1 computer. 33% of the time, they sold 2 computers, okay? So when I take those probabilities, it's empirical, experimental, all right? You would be given the actual data here, or you would actually perform the experiment. And we take those probabilities and we turn them into a probability histogram. All right, so next we're going to look at the sum of two dice. So just remember to take a look at this chart if you need to. We have a roll of one die on the left and the roll of the other die up across the top. So you can consider the two dice to be red and blue, so they are very different, okay? So using that chart to calculate the probability of each of our different outcomes, I can roll anywhere between a 2 and a 12. You can see that the 2 appears once, the 12 appears once, all right, 11 is on there twice, 10 is on there 3 times, all right? So 1 out of 36 is the probability of rolling a 2, 2 out of 36, probability of rolling a 3, etc. All right, 7 is my most common value. It shows up 6 times on the chart, so 6 out of 36 times. And then again, my probability histogram for the theoretical probability of getting the sum of two dice. Okay. Now, we often look at something called expected value. This is where we want to use the probabilities and the outcomes to calculate the expected value or the average value, the average outcome that we would expect to get. And what we're going to do is we're going to take the outcome, so that's my X values, times the probability of getting that outcome. Okay, and then we're going to add to that the next outcome times the probability of getting that outcome. So if you remember back to our one variable statistics again, this should look like a weighted mean, all right? It's the sum of the outcomes times the probability of those outcomes. So in the weighted mean, we had the value times its weight and adding all those up. Same thing here. So we've got the outcome is the number of computers sold, the probability of that outcome. We multiply across the rows, we add up all these values, and I get an expected value of 2.6. So what does that expected value of 2.6 actually mean? Well, what it means is that we will sell approximately 2 to 3 computers per day. That's what's my expected. I expect to sell 2 to 3 computers each day. All right. Now, sometimes certain probability experiments can also have values associated with the outcomes. So for example, we might have a dice game where I'm rolling a single die and I would add points for an even number and I would subtract points if I roll an odd number. So now my outcome is not what I roll. My outcome is the number of points that I score. So I've got a third column in my table. I've got the value that I roll, the points, which is now my outcome. You can see this is labeled X. Okay, points. Remember, odd numbers, I lose points, so it's negative. Even numbers, I gain that many points, so it's positive. All right. My probabilities, remember this is a uniform probability distribution, so they are all 1 out of 6. And to find the expected value, I'm going to multiply the points times the probability and then add all those values up. So here we are, -1 times 1/6 plus 2 times 1/6 on through the chart. I get an expected value of 0.5. And a common question, is this a fair game? And your answer should be no. All right. If this is not 0, your answer will be no. So this is a definition of a fair game, is the expected value must be 0 for a game to be fair. Okay. Any other value, your answer will be no. This is not a fair game. All right. So that's your probability distributions lesson. There's some homework in the textbook, and we will take this up in class tomorrow. Have a good night.